platform. I'm a university academic at Curtin University. I'm trained as a chemist, but I have a passion for teaching and education, and recently had an opportunity to do some work exploring using immersive virtual reality to help students visualize chemical concepts. So the talk will talk about what we've done in VR, how we designed the activities, and some of the chemistry learning we were hoping to get. So a little bit of chemistry. I don't know how many people are chemistry teachers, but it's a focus on our design more than anything else and what we did. Okay.
And I wrap up slide by slide, and I will translate to Korean and
Okay.
shortly. And 이제 마우로 교수님은 지금 서울대에 지금 잠깐 오셔가지고 협업하고 계시고 물리교육과 송진훈 교수님 방에서 이제 협업하고 계시고요. 내일이면 또 20명의 커튼대학교 학생들이 서울에 방문해요. 그래서 같은 서울에 있어가지고 이렇게 세미나를 열 수 있었던 거고, 마우로 교수님은 뒤에 슬라이드 혹시 보신 분들은 아시겠지만 화학교육 베이스로 하셨어요. 케미스트리 베이스로 하시고 어떤 분자 구조를 이거를 시각적으로 바꿔보고 어떻게 배울 수 있는지 VR을 적용해서 배울 수 있는지에 대해서 했었고, 그냥 저도 간단하게 말씀드리면은 저는 호주 커튼대에 이번 여름에 가서 이 세 개의 프로그램을 체험했었고요. 이 연구 결과에 대해서는 못 들었었는데 또 PPT 보면서 하니까 또 알지 못하는 것들도 알게 되고, 그리고 실제로 어떻게 이런 배움이 VR을 통해서 일어날 수 있는지에 대해서 실제로 연구하신 결과를 가지고 오셨으니까 꼭 화학 베이스가 아니시더라도 많은 도움이 되실 거라고 생각됩니다. 네, 들어보겠습니다. Okay, you can go.
Okay.
Go on.
Thank you. So okay, now the slides aren't changing. Oh, okay. Now they're working. Right. So to start, one of the important things in chemistry is that students need to be able to visualize what's happening. Chemistry is often seen as difficult because we need to visualize on three levels: the macroscopic, the symbolic, and the submicroscopic. Now, what we mean by this is the macroscopic is what we can measure, what we can observe. So they're observable properties: melting points, boiling points, color, density, things like this. The symbolic representation is how we describe the chemistry with symbols, formulas. It's kind of the language of chemistry. And submicroscopic is what's actually happening at the atomic or molecular level. Now,
이 세 가지로 시각화를 하고 계시는데요. 마크로스코픽은 이제 거시적인 눈으로 관찰되는 그런 현상들, 좀 작다고 보면 작을 수 있겠지만 눈송이나 이런 어떤 멜팅 포인트에 대한 용해도 아니면은 녹는 점 그런 것들을 관찰하고 이런 것들을 하는 것이 거시적인 것의 시각화이고, 그다음에 상징적인 거는 어떤 심볼릭한 것들이죠. 화학적 현상의 기호 아니면은 표현 그런 것의 상징적인 거고, 서브 마이크로스코픽이 초미시적인 것이라고 저는 해석을 했는데 현미경 좀 이하의 수준, 현미경으로는 광학 현미경으로는 관찰이 되지 않는 그런 초미시적인 수준의 것들을 시각화하기로 되어 있는데, 마우라, can I give you a question?
Yes.
Right. And I don't when I translate these slides, and why did you categorize this three kind of visualization? Why did you categorize it like this?
It's not my categorization.
Uh-huh.
It was a categorization suggested by a chemistry educator maybe 40 years ago,
Mm-hmm.
and it's helped chemistry educators structure the way they teach and what we do. So it's Alex Johnston, the chemistry educator from Scotland. He suggested this triangle, and it seems to fit quite well. You can do something similar with physics, in the same sort of way. Whereas in submicroscopical physics would be forces.
오케이. 뭐 이런 것들은 마우로 교수님이 하신 건 아니고 여기에서 물리에도 적용이 되는 그런 것이라고 막 얘기를 해주시는데 좀 빠진 게 있을까요, 수민 쌤? Perfect.
Okay. So
아, 네.
if anyone wants to ask a question while I'm speaking, don't wait to the end. Feel free to interrupt.
네, 중간에만 이제 질문하셔도 된다고 합니다. 그러면 수민 쌤께서 번역해 주실 거예요.
Or
네,
put it in the chat and we'll talk about it later.
네. 채팅창
Okay.
괜찮고요. 네.
So when we talk about the submicroscopic level, the problem with this is we can't observe it. We only imagine. We can help students imagine this with diagrams or simulations, but they need to imagine to understand the concepts, to develop mental models, to be able to predict. And that's one of the reasons for science. So you being able to predict what's going to happen. You can't do that if you don't know what's happening at the molecular level.
네, 혹시 네, you've done talk about this slide?
Yes.
오케이. 혹시 제가 이해하기로는 여기에 초미시적인 그런 세계에 대해서는 관찰 불가한 것들, 그러니까 막 과학 현미경으로 불가한 것들이 초미시적인 세계다라고 이렇게 했고요. 이것은 상상력으로만 접근 가능하고, 이해하기 위해서는 어떤 시뮬레이션이나 그림들이 도움이 되고, 그리고 이런 것을 학습자가 다음에 내용을 학습할 때 정신 모델이라고 하는 것은 좀 머릿속으로 모델이라는 것은 정신 모델 모형이라는 것은 머릿속으로 상상한 현상에 대한 뭐 그림이나 어떤 컨셉 같은 걸 말하거든요. 정신 모델을 뭐 개발하고 그다음에 또 거시적인 세계, 관찰 가능한 세계에서 이제 관찰한 것들과 이러한 내 머릿속의 개념과 연결을 하고 그렇게 연결한 것을 또 상징적인 구조로 또 연결을 해가는 과정에서 이런 그 미시적인 것들이 이제 시각화할 필요가 있다라고 얘기를 하고 있는데 수민 쌤 혹시 뭐
저는 계속 프리딕트 얘기를 하셔가지고
네네.
이걸 알아야지 어떻게 될지 그 거시적인 세계에서도 이 미시적인 거를 어떻게 되고 있는지 이해를 해야지 거시적 세계에서도 예측을 할 수 있다. 그 이후에 어떻게 될지 이렇게 이해했습니다.
감사합니다. 역시 제가 딴 생각 잠깐만 해서 감사합니다. 네, you can go on.
Okay. If you want, I just realized because we are going to be translating the slides, as I talk, the talk will go for significantly longer than an hour. That's okay for me. If you would like to just focus on the virtual reality stuff, I can skip the first 10 or 15 slides that talk about the background of why we need to visualize in chemistry.
혹시 뭐 1시간 이상이 되면은 나가셔야 될 분이 계실까요? 그럼 조금 길더라도 그러면 한 발짝 한 발자국 이제 한 슬라이드 한 슬라이드 하면서 해도 괜찮을 것 같네요. There's no person who are hurry, so
Okay.
so
Yeah,
you
I
can
don't mind
go.
going slowly,
네.
but you told me an hour, and I
Uh-huh.
don't want to keep people here for an hour and a half if they're expected to for an hour. Okay, so we move on to the why it's important to understand the submicroscopic, because if you understand that, then you can explain what it means by pressure of a gas, or what happens when a liquid boils, what happens when you put sugar or salt in water, and why does it dissolve? And if you can see the molecular level in your mind, it can explain the chemistry.
혹시 수민쌤 그냥 해주실래요?
네, 여기 나와 있는 것들을 이제 그 작은, 그 광학현미경으로 볼 수 없는 그 극미시적인 부분을 이해를 해야지 저희가 실제로 관찰할 수 있는 뭐 가스의 이제 그 압력이라든지 아니면 왜 그 액체가 끓는지 아니면 이제 뭐 솔트를 이제 그 넣었을 때 왜 용해가 되는지 이런 것들을 이해를 할 수 있다라고 얘기를 해주신 것 같아요. 그래서 분자적인 그 부분은 우리 머릿속으로 이해를 해야지만 우리가 볼 수 있는 그 현상들을 이해를 할 수 있다라고 얘기하신 것 같습니다.
네. 제가 하니까 한 다음에 또 막 이제 시간이 더 늘어날 것 같아가지고 and Sumin will translate your your slide.
Okay.
Okay, thank you.
감사합니다. Okay. Oops. So this table here is a table that I think certainly most elementary school children can fill in. No, certainly most middle school children can fill in. The elementary school, possibly not. But even at the high school level, many students can fill the table, but they can't explain why a liquid has a variable shape. Why is a liquid incompressible? Why is a solid incompressible? But why does a gas have a variable volume, a variable shape, and also very compressible? They need to have a submicroscopic image to be able to explain this.
네. 그래서 이제 초등학교, 뭐 중학교, 고등학교 다 마찬가지로 아이들이 그 이런 현상들을 봤을 때 고체는 말 그대로 고정이 되어 있고 액체는 뭐 모양이 다양하고 이거는 당연히 알고 있지만 뭐 이제 여러 가지 이런 것들을 통해서 알 수 있지만 왜 그런지에 대한 이해나 아니면은 설명을 하기는 조금 어려워한다라고 얘기를 하셨던 것 같아요. 그래서 그거를 이제 이해를 하기 위해서 그 극미시적인 저희가 볼 수 없는 이제 분자적인 그런 접근이 그 왜 그런지를 그 이유를 설명하기 위해서 꼭 필요하다라고 얘기하셨습니다.
감사합니다. Okay. This slide is the words for the previous slide. Okay. So we can show with an animation.
When heat is applied to a sample of water, phase changes occur at 0.
We don't need the volumes. So we can show the students a video like this where they can see how the particles are moving. But research has shown that this by itself is not very useful. You need to, if you show them a video like this, you need to ask them questions to get them to actually pay attention to what to observe. For example, what is the difference in movement when the particles are in stage 1 and stage 2? Or what's the space between the particles in stage 5 and stage 4? Or stage 5 and stage 3? So if you ask them questions about what they're supposed to look at, then they can learn from it. If you just show them the video, they don't know what to observe.
아이들한테 지금 방금 전에 보여드렸던 이런 비디오의 어떤 이런 그 움직임이라든지 이런 것들만 보여주었을 때는 아이들이 무엇을 집중해서 봐야 하는지를 아이들이 모르고 저희가 질문을 통해서 이제 유도를 하는 수밖에 없다라고 말씀을 하셨어요. 지금 보여드렸을 때 아이들이 여기 이거를 그냥 보면서 내가 뭐에 집중을 해서 봐야 되지? 뭐를 관찰하라고 하는 거지?를 아이들이 알게 하기 위해서는 말 그대로 교사가 이제 질문을 5랑 4랑 뭐가 달랐니? 혹은 어떤 게 변화가 됐니? 이런 것들을 계속 질문을 해야지만 아이들이 여기서 어떤 거에 집중을 해서 봐야 되겠구나라고 알 수 있다라고 말씀하셨습니다.
No, next slide. Okay. So another example of chemistry in context where if they can visualize what's happening, they can explain why clothes dry. Most students will know that water boils at 100 degrees. They also know that when it's boiling, the water is going from a liquid phase to a gas phase. But clothes dry on the line, even on very cold days. If you hang your clothes on the line, they dry. Why do they dry when it's less than 100 degrees?
아이들이 이제 왜 여기 나와 있는 거 그대로 설명을 해주셨는데 물에 아이들이 이제 이거를 그 비주얼라이즈를 해야 하는 이유가 왜 그런지를 이제 깨달아야 된다라고 얘기하시면서 그 예시를 하나를 들어주셨는데요. 물에 끓는 지점은 100도인데 이런 날에도 빨래를 이제 줄에다가 걸면 항상 마르잖아요. 그 말 그대로 이제 이 기체화가 일어나게 되는 건데 왜 그런지 그러면은 물을 어떻게 돼가지고 이런 것들이 일어나게 되는 건지 이런 것들을 설명하기 위해서는 꼭 그 시각화가 필요하다라고 이제 그 하나의 예시를 들어주신 것 같습니다.
Okay. One way we can do this is by showing them an animation. Again, this is something done by one of our team where the students can see the water molecules moving around in a liquid, and at the surface, they can see some molecules leave, but some come back. And there's always, it crashed. Okay, I will restart.
Yeah.
Okay, can you see my screen? No.
Oh.
Let me go back to I might move to the next slide because I think that video is a problem. We'll switch displays. Okay. So on the previous video.
Oh, I cannot see your screen yet.
Oh, okay. I forgot to actually press this share. Okay, share.
Okay. Oh, now I can see.
No, not that one. Stop share. Share this one.
Okay.
Okay.
Yeah.
Right. Okay, good. So For the previous one where they showed the water molecules moving and some leaving and some coming back, again, the developers found that without questions to interrogate what they observed, the students didn't know what to observe. They just looked at pretty pictures and balls moving around.
네, 방금 전에 그 잠깐 끊기긴 했는데 보여주셨던 그 영상이 이제 팀에서 이제 만드셨는데 거기 보면은 물 분자가 이렇게 떠났다가 뭐 다시 돌아오는 것도 있고 그런 이제 애니메이션을 만들어서 이제 아이들에게 보여주셨을 때 아까 전에 말씀하셨던 것과 마찬가지로 아이들은 그거를 봤을 때 즉 선생님이 이거를 보세요, 뭐 떠나는 걸 보세요, 뭐 물 분자의 그 뭐 표면을 보세요 이렇게 얘기하지 않으면은 그냥 말 그대로 그 영상을 보면서 어디에 집중을 해서 봐야 되고 어떤 거를 봐야 되는지에 대해서 인지하지 못하고 말 그대로 선생님께서 계속 그 질문을 던져주셔야만 아이들이 무엇을 이제 집중해서 봐야겠다라고 생각을 할 수 있다라고 방금 그 애니메이션 영상에 대해서 얘기해 주셨습니다.
Okay, so because of these, we were looking at the advent of immersive virtual reality, looking to what can we do with virtual reality that will help students visualize. And the immersive virtual reality, or just virtual reality, has the advantage that we can do things that you can't do on a 2D screen. You can walk into a molecule, you can change your representation, move it around much more readily. You can visit places that are not possible under normal circumstances, and that includes the molecular world or the astronomical world. So they are the advantages that we think virtual reality can offer.
이제 가상현실이 줄 수 있는 긍정적인 점에 대해서 말씀을 해주셨는데요. 이제 어떤 점에서 시각화나 이런 것들이 긍정적인 면이 있는지에 대해서 말씀을 해주셨어요. 여기 나와 있는 것처럼 물 분자에 가까이 가서 다가가서 보고 그리고 그걸 한번 움직여 볼 수도 있고 아니면은 불가능한 이런 장소들에 방문을 할 수 있고 이런 것들이 굉장히 큰 장점이다라고 얘기를 해주셨습니다. 분자적인 어떤 그런 공간에 갈 수도 있고 아니면 우주 공간이라든지 이런 평소에서는 방문할 수 없는 이런 장소들을 방문할 수 있는 것이 굉장히 큰 장점이다라고 얘기해 주셨습니다.
Okay, so these are the words to explain the previous slide. So what we did, we developed 3 virtual reality activities, and some videos can be found on the YouTube channel. The first one was investigating snowflakes. Why do they have hexagonal symmetry? And so to understand that, they need to understand how the water molecules are interacting. So that's a key component in the chemistry, the hydrogen bonding, also important in biology. Then we had an activity that was looking at the effect of shape on physical properties, and we used the taste receptor and the fact that 2 mirror image forms of the same compound have very different tastes. One is sweet and one is bitter. And the final one, we got the students to investigate why enzymes are such good catalysts. So there was a chemistry, and all 3 had, in some respect, similar themes in that how molecules interact with each other and how does the shape and charge of a molecule influence the chemistry.
네, 이제 요게 세 가지의 이런 것들을 이제 개발을 하셔서 이 유튜브 채널에서도 활용을 할 수 있나 봐요. 먼저 첫 번째로는 눈송이를 이제 직접 조사를 할 수 있는 이런 활동이 나와 있고, 이 눈송이가 왜 그 육각형이면서 이 대칭을 이루고 있는지에 관련해서 우리가 이거는 이 육각형 대칭을 가르고 있는 이유가 물 분자의 서로 그 어떤 작용 때문에 일어나는 것이구나. 이런 것들을 이제 그 VR을 통해서 확인을 할 수가 있고, 이제 그 얼마나 응집력이 있는 있는지, 얼마나 끌어당기는지 이런 거나 아니면 어떻게 결합이 되고 있길래 이런 모습이 나올 수가 있는지에 대해서도 확인을 할 수가 있고, 또 여기 나와 있는 이 밑에 이제 미각 수용체와 관련해서도 서로 이제 다른 그 쓰거나 아니면 달거나 한 것들이 이제 작용이 어떻게 일어나는지 마찬가지로 이 효소 이 기질에서도 왜 이것이 굉장히 좋은 촉매제가 되는지에 대한 것들을 분자적인 관점에서 이해를 할 수 있게 해주는 이러한 그 활동들이 있다라고 설명해 주셨습니다.
Thank you. Okay. When we designed our activities, we decided to have, we followed Deed's example, and we tried to have in everyone some thinking about how virtual reality could impact the senses. So using visual, obviously, but audio, and also with the handsets, the haptic component. We wanted them to do things in virtual reality space, not just watch an activity. And the activities also had to have a narrative, a task, and a meaning for why they were learning. A little bit like a quest in a game. For the snowflakes, the quest was, why do snowflakes have hexagonal symmetry? And then we gave them a series of activities that started very basic and moved them to a position where they could answer that question. And we also believe that learning is a social endeavor. So we designed our activities to have two people in the virtual reality space together. So they were working on the problem together. They could see each other, they could talk to each other, and they built their knowledge together.
여기 나와 있는 내용들을 보면은 일단은 이 벌추얼이라는 것 자체가 굉장히 감각적으로 감각적으로 다가가는 그런 부분들이 있기 때문에 그냥 말 그대로 그냥 보는 것뿐만 아니라, 어떤 그런 감각적인 그런 여러 가지 감각들을 한꺼번에 복합적인 요소들이 들어간다라고 말씀을 해주셨어요. 그래서 그냥 보는 것뿐만 아니라 직접 이 센스 감각적인 요소들, 여기 나와 있는 바대로면 시각, 청각, 촉각 이런 것들이 한 번에 이제 작용하는 그런 것들이 있고, 또 두 번째로는 이제 내러티브, 굉장히 의미를 잇는 그런 어떤 그 과제들을 이제 제시를 해주고 싶다라고 얘기를 하시면서 그 퀘스트 얘기를 하셨어요. 전 게임에서 해결을 해야 되는 그 퀘스트 말 그대로 과제 같은 그런 부분들이 있고, 아까 전에 말했던 그 눈송이를 조사하는 거기에서는 말 그대로 눈송이가 왜 그러면은 그런 모형을 이제 나타내는지에 대해서 아이들이 물분자를 이제 그 기점으로 조사를 해 나가야 되는 거죠. 그게 하나의 이제 퀘스트가 될 수 있고, 이게 이제 내러티브적인 어떤 그런 의미 있는 그런 학습의 내용이 담겨 있고, 그리고 또 마지막으로 이제 사회적인 요소. 그러니까 말 그대로 혼자 이제 하는 게 아니라 둘이 같이 상호작용을 하면서 서로 얘기를 하고 함께 문제를 해결해 나가는 그런 소셜적인, 사회적인 그런 요소도 가지고 있다라고 얘기를 해주셨습니다.
Okay, thank you. Okay, so when we were working with virtual reality, we kept asking ourselves the question, what can we do better with the technology? Not just if it can be done on a 2D screen or can be done with models just as well, why use expensive technology? So the virtual reality gives us the opportunity to visualize chemistry at the molecular world, which is not so easy with other methods. We can view 3D structures, again, on a 2D screen. It's not the same, even with the appropriate goggles. And we could work with very large molecules or very large collections of molecules. With the water molecules, they were working with 150 molecules. You can't do that with models. 150 is too many. And so they could see and feel things that couldn't be done on a 2D screen or with models.
이제 2D와의 그 차이를 얘기를 해주셨는데요. 그렇다면 우리는 기술을 통해서 어떤 거를 이제 더 잘할 수가 있느냐라고 말씀하시면서 이 비싼 기술을 이용하면서 이게 2D랑은 어떠한 차별점을 가지고 있는지를 생각을 해야 한다라고 얘기를 해주시면서 그 화학적인 것에서 일단은 기본적으로는 어떤 분자적으로 이제 잘 접근을 할 수 있는 것에 대해서 반복적으로 얘기를 해주셨어요. 그래서 2D와 비록 그 같은 그 그거를 가지고 있다고 하더라도 훨씬 더 큰 여러 가지 좀 더 이렇게 큰 내용으로 이제 접근을 할 수 있고 훨씬 더 그 분자라든지 이런 것들도 더 집합적으로 접근을 할 수 있고 라고 얘기하면서 이제 구체적인 수치도 훨씬 더 크게 이렇게 접근을 할 수 있다라고 얘기를 해주셨습니다. 그리고 이런 부분들이 2D에서는 볼 수 없을 만큼의 어떤 그 규모라든지 이런 것들을 자랑할 수 있다라고 얘기해 주셨습니다.
조금 더 첨언하자면은 이제 150개 정도의 그런 분자 구조를 한꺼번에 이제 관찰할 수 있는데 여기에서 실제로 피지컬적인 그런 모델들 가지고는 150개를 할 수 없지만 이 3차 공간에서는 150개의 그런 모델을 가지고 작업도 컴플렉스한 그런 분자들도 다룰 수 있다라고 얘기를 해주셨습니다. 네.
Okay. With the actional component, we wanted the students to be doing things. So in the virtual reality space, they were building molecules, they were moving them around, placing them into the taste receptor or placing the molecule into the reactive site of an enzyme. So they were moving around, they were picking things up, they were making things happen. It was at no stage were they just watching a movie or an animation occur.
이런 요소들에서 가장 중요한 거는 직접 해볼 수 있다라는 건데요. 직접 아이들이 이 분자를 뭐 만들고 아니면은 직접 움직이고 내가 원하는 곳에 위치시킬 수 있고 아니면은 이제 뭔가를 고르거나 아니면은 직접 반응을 보거나 이런 효소에서의 그런 반응을 보거나 아니면 직접 일어나게 만들게 하거나 이런 것들이 아까 전에 얘기했던 그 애니메이션이나 아니면은 무비 어떤 그 동영상을 그냥 보고 있는 것과는 확연한 차이가 직접 한다는 것에서 확연한 차이가 있다라고 얘기해 주셨습니다.
For the narrative, again, I think, and most of us believe that if the student has a reason to learn, curiosity that they want to find out, they will learn more effectively. They will pursue that process. So we tried to give them a story, a narrative. For the taste receptor, for example, we use the amino acid phenylalanine. There are two forms, mirror image forms, like your left shoe and your right shoe. One form tastes sweet, the other form is very bitter, but they're just mirror images of each other. And so the same formula. We get them to taste it and then say, why do these two things taste so differently? They have a reason to learn, and then we put them into virtual reality through a series of activities. They can come to the conclusion and understand why one is sweet and one is not.
여기서 아이들한테 그 내러티브라는 게 이제 하나의 이제 스토리를 얘기를 해주시는 스토리를 말씀을 해주시는 것 같아요. 아이들이 배우고자 하는 그 왜 배워야 하는지에 대한 그 이유를 제공해주면은 훨씬 더 그 학습 효과가 뛰어날 것이다라고 얘기를 해주시면서 호기심을 충족할 수 있는 그런 것들을 준다면은 그런 어떤 스토리 라인을 이제 준다면은 훨씬 더 효과가 극대화될 것이다라고 얘기를 해주셨는데요. 그 이제 맛의 어떤 그 수용체도 마찬가지로 이제 단 것과 쓴 것이 같은 그 포뮬러를 가지고 있음에도 불구하고 다르게 느껴지는 이유가 무엇일까를 아이들한테 이제 스토리를 제공을 하고 그것을 이제 아이들이 그 해답을 찾아 나가는 과정에서 이제 활동이 주어지고 그것의 어떤 결과를 직접 내보는 그런 과정 자체에서 이 스토리가 제공이 되고 내러티브가 제공이 되면서 거기서의 효과성이 좀 크게 나타날 수 있다라고 얘기해 주셨습니다.
Thank you. And the final aspect of the activity was they were always working together in pairs. So each student could see the other students head in the form of an avatar and two hands, and they could obviously see their own hands, so they knew where their partner was, and we wanted them to talk to each other, explain their thinking, so that check with your part with the students would be asked by the program, what do you think is happening here? Explain to your partner, how do you agree or disagree? So that we tried to design the activity that required teamwork.
항상 여기에서 이제 마지막 그 측면으로는 항상 이제 그 아까 전에 말씀드렸던 그 사회적인 부분, 항상 둘 이상이 이제 페어로 같이 활동을 할 수 있게 해야 한다고 말씀을 하셨어요. 그래서 직접 어디 있는 그 짝이 이제 어딘지 보고 어떻게 하고 있는지를 직접 보고 하면서 설명을 하게 하고, 또 교사가 여기에서 지금 어떤 일이 일어나고 있는지 서로에게 한번 설명을 해보세요. 이렇게 항상 페어로 할 수 있게 서로 교차해서 질문을 하고 이런 이런 측면들을 계속 강조를 해야 된다라고 말씀을 하시면서 뭐 어떤 점에서 동의하니 아니면 서로 어떤 점에서 동의하지 않는지에 대해서 서로 한번 얘기해 보세요. 이렇게 얘기를 하기도 하고, 그래서 항상 이런 것들을 만들어낼 때 수업을 이제 구성하고 아니면 미리 이제 계획을 할 때 이렇게 서로 상호 이런 것들을 할 수 있는 그런 활동들을 만들어야 된다라고 말씀을 하셨습니다. 같이 할 수 있는 활동을 항상 디자인을 해야 된다라고 말씀하셨습니다.
질문이 있는데요.
네.
네. I have a question. So at the same time, only two people can view the same screen.
Well, at the time, yes, because two people were in virtual reality space. They had the headsets on and they could view and manipulate the objects in the virtual reality space. Now with the technology, you can do more than two. But when we started in 2020, two was, even that was not easy. I think with the Meta 3, you can have multiple people in the same space viewing and interacting with the same objects. But at the time when we developed this, two was a lot.
혹시 더 질문?
You can tell the circumstances of your device's spec. You can tell your device. You can introduce.
It's an HCT 5.
5.
But we bought these as the state of the art in 2020, and we use the same ones for our data collection and developing the programs. And so now they are a bit old-fashioned and the technology is not so good. We need a lot more hardware to do that than you can with things like the Apple View and the Meta devices.
It's more meaningful than any other apps.
Well, yeah, we focus on the education aspect, not so much the entertainment and the motivational aspect. Even though they were motivated, that was not the key focus.
Yeah.
Okay, let's move on to what we did. Hydrogen bonding is a concept that that's important in physical properties of many molecules and the chemical properties. DNA is shaped like DNA because the double helix, because of hydrogen bonding. Water is a liquid because of hydrogen bonding, even though it's a very small molecule. And many of the biological processes are influenced by hydrogen bonding. So, and it's taught at school, in middle school, I think in Korea, and certainly in lower high school in Australia and upper high school. But many of the students do not understand the concept very well. They understand it well enough to answer typical exam questions, but not when we ask them beyond the typical exam questions.
이 결합이라는 그 이게 개념 자체가 굉장히 중요하고, 왜냐면 이런 것들이 화학적인 어떤 DNA라든지 아니면 물이라든지 이런 것들에서 굉장히 중요하고, 또 그 생물학에서도 굉장히 중요하게 다루어지고는 하는데, 이런 물도 마찬가지로 이런 그 수소와 그런 결합들이 굉장히 중요한 개념으로 작용이 되고 있음에도 불구하고, 한국에서는 중학생부터 이거를 가르치는 것으로 알고 있는데, 개념에 대해서 조금 더 구체적으로 이해하지 못하고, 말 그대로 전형적인 어떤 시험 문제를 푸는, 네, 딱 그 수준에서만 머물러 있는 것 같고, 그 이상을 물어봤을 때 아이들이 대답을 하지 못하는 그런 경우들이 좀 많다라고 얘기해 주셨습니다.
Okay, so this is what we did. When we had the students, we developed the curiosity why are snowflakes hexagonal symmetry, and most Australian students had never seen snow. So for them, snow was novel. And so we asked them about that. They put the goggles on, and when they put them on, they were standing in a snowfield with snow falling down. Then we moved them through activities. First, observing the interaction of just two water molecules, then placing the water molecules, how many around the central water molecule. They built a layer of ice and then put the layers together to make a lattice with 150 water molecules, and then looked at that to see how it related to snowflakes.
일단은 학생들이 제가 잘 이해를 한 게 맞나요? 눈을 본 적이 거의 없어가지고 네, 그래서 아이들한테 이제 곡을 씌우고 했을 때 아이들이 그 눈의 어떤 그 눈 평야의 설원에 있고, 그리고 눈이 내리는 것을 일단 먼저 보게 하고, 그 다음에 이제 물 분자가 처음에는 두 개가 결합을 하고, 그 이후에 그 중심축을 이뤄가지고 그 옆에 얼마나 많이 붙는 거를 보게 하고, 나중에는 그것이 격자 무늬를 이루어서 결과적으로 그 눈송이의 그 대칭적인 그 육각형의 대칭적인 그 모양을 가지고 있는 것까지를 이제 단계적으로 보게 했다라고, 네, 저는 이해를 했습니다.
네. 조금 보충하자면은 이제 호주 거기 퍼스라는 지방에서 이제 교수님 오셨는데 커튼 대학교가 있고 거기는 최고 what is the most highest degree is in Perth? What is the most highest degree is
The hottest temperature, the
hottest
coldest temperature is zero.
coldest temperature is zero.
Zero.
맞아. coldest
Never minus.
마이너스가 없어서 막 거의 눈이 안 오고 막 그래가지고 이번에 커튼 대학교에서 오는 학생들도 이제 눈 쌓여 있길 바란다 막 이렇게 하면서 하더라고요. 그러니까 막 그렇고 이제 코어 이제 물 분자가 있고 그게 이제 연결이 되고 그것이 레이어를 이루어서 이제 쌓이게 되고 하는데 하기 전에 눈도 처음 보니까 막 그런 것을 눈의 경험을 조금 하고 막 이렇게 거의 observe 돼가지고 조금 몰입해가지고 이런 활동을 더 할 수 있었다라고 저는 좀 들었었습니다. 네.
Okay,
go on.
We have some videos of what the students are doing.
Like so. Try to adjust.
It's thinner.
Yep.
And very close. It becomes thick. But if it gets too close, it becomes thin again. So it's an optimal position.
Okay, let's change this. Yeah, if I change the angle, the colors change. Like so.
Oops, no. Yeah.
Okay. You can.
Oh, sorry.
You can share again. No problem. Video has some sort of problem.
I hope this doesn't happen with every video.
It's okay. Take your time. 네, 저도 막 그걸 해봤는데요. 거기 가가지고 실제로 각도에 따라서 이제 아까 보셨다시피 각도에 따라서 그런 잘 맞냐 안 맞냐 막 이런 것이 나왔었고 아까 미각 수용체에 대해서 설명해 주셨던 것처럼 그것도 미각 수용체도 이제 같은 이소토머라고 하죠. 막 같은 건데만 이제 조금만 모양이 바뀌면은 맛이 달라지고 성질이 달라지는 그런 분자에 대해서 설명을 했던 것 같습니다. 네, you can go on.
Okay, so this is another activity they did.
We have 3 layers of ice and we want to connect them. You got this. There you go.
okay. 그래가지고 이제 레이어를 하나 하고 그다음에 그것을 또 붙여가지고 눈의 결정이 생겨가는 과정을 영상으로 이제 보여주신 거고 여러 명이서 같이 한 화면에 들어가서 체험할 수 있었습니다. 2명까지밖에 아까 막 수연 쌤께서 얘기했던 것처럼 2명까지밖에 안 됐었고요. 막 이제 독립형이 아니라 선이 들어가 있는 그런 HTC 바이브 가지고
So
구성을.
do you think it might be worth trying on your computer?
Okay. I'll try.
You've got
my-
the slides,
Mhm,
and then
okay.
maybe your computer's a better
Okay.
quality than mine.
I will try. Okay, now you can see the
Yep.
Can you see the slide?
Yes, I can see the slide. Yes.
I will
Scroll down to
scroll down to okay. The slide is before slide.
this one. Yes, this
Okay.
one. They can't hear the voice.
You cannot hear the voice. Okay. Sorry. Okay. So.
We have 3 layers. It's
Right
all
here?
hexagon
Yes.
Okay.
everywhere. I guess that's explaining this.
Why they're all hexagonal?
Yep.
Okay. Can I move on?
Thank you. Yes, please. Okay. This is a complicated slide, but just to try to show you, just focus on the left-hand column. And the students who understood well are down the bottom in category 3, category D, and those who understood poorly are in category A. So before the activity and after the activity, you can see that most students improved having done this activity. There were a couple of students who didn't improve and 2 that got worse, but of the bulk of the students, they got better from before to after. And that's in the second and third columns, they're the same as well. So the key message is the understanding of the chemistry improved dramatically, except the people who were very poor at the beginning.
여기 있는 그래프에서 왼쪽을 조금 중심적으로 이제 보시면은 이제 D 같은 경우에는 이제 원래 잘하는 학생들, 그리고 A 같은 경우에는 조금 이제 미흡한 학생들인데, 어찌되었든 이렇게 보면은 거의 다 향상도를 많이 보이고 있다라고 말씀을 해주셨어요. 뭐 맨 처음부터 잘 못했던 학생들 몇몇을 제외하고는 대부분은 이제 향상이 많이 되었고, 그리고 이런 이런 드라마틱한 이런 향상도를 이제 보이는 거에서 아이들이 화학적인 이해 능력이라든지 이런 것들이 상승을 했다라고 생각하시면 되고, 가운데 있는 것도 마찬가지고 처음에 정말 못했던 친구들을 제외하고는 거의 다 많은 향상도를 보였다라고 이게 키 메시지라고 이제 얘기를 해주셨습니다.
I have a problem with this slide, and when what's the difference of second column and third column?
Well, the second club was many students at the beginning. Before we did the VR, we interviewed them to see what they understood. And although the two students were sitting next to each other, we asked them individually and we got them to write their answers individually. And so the first column they worked individually before and they worked individually after to answer the questions. The second column, they worked individually before, but afterwards they worked as a team. So they provided only one set of answers. And the third group, they worked as a team at the beginning and they worked as a team at the end. So that's just looking at, rather than try and put everyone together, some people worked as a team and we thought we should separate that data.
Why did you experiment it like this?
Well, we chose not to put them in separate rooms. We asked the question with the two students next to each other, and most of them wrote their own answers down. And then when they started to speak, they gave their own interpretation. But in some cases, you had students where they looked at the other person and they could see what they were writing and they were writing the same thing. Or when we asked the question to one student, the other student says, I agree with him or I agree with her. And so they weren't demonstrating individual knowledge, they were always sharing that information. And we couldn't separate that, except to interview them separately at separate times. But that was against the idea of them working together in virtual reality.
수민쌤, 네, 제가 이해한 거는까지는 이게 두 번째 컬럼은 인디비주얼하고 컬래버레이터하고 그다음에 이거는 컬래버레이터하고 컬래버레이터 둘 다 사전 사후에 이렇게 진행했다는 거고, 네, 왜 했다는 게 제가 잘 못 알아듣겠어가지고 혹시
저는 이제 혼자 이렇게 하게 할 때 옆에를 보고 쓰기도 하고, 그냥 둘이서 이렇게 하게 되면 옆에를 보고 쓰기도 하고, 아니면 그냥 본인의 개인적인 해석을 내놓기 전에 그냥 옆에 있는 아이한테 저는 그냥 동의해요, 이렇게만 얘기하는 학생들도 있어서 이제 혼자 데몬스트레이트를 하게 했는데, 이게 마지막에는 이게 또 같이 하게 하는 VR의 어떤 아이디어와는 조금 상충되는 면이 있다, 이렇게 얘기하신 걸로 들었어요, 저는.
저도 질문 하나 또 해도 될까요?
네.
I have another question. If the visualization and interaction are important in immersive learning, would using a well-implemented 2D program can be as effective as using 3D VR? What do you think?
We tried that. One of our students was looking at comparing physical models, 2D program that modeled interactions with water, and virtual reality. Most students did not like the 2D program and they found it very difficult to move things around, and the learning seemed to be more, they were using more energy to work out how to use the software than to learn the chemistry. Whereas in virtual reality, you didn't need to do that. If you wanted to pick the molecule up, you put your hand out, you press the button, and you could pick it up. So manipulating the molecules, moving them around was so much easier than the 2D. And they had difficulty seeing the key message we wanted them to see on the 2D program. Even though chemically it was a very accurate program, it was just much harder to see.
Thank you. So you mean in 3D, 3D program, right? More than 2D program.
It was on a 2D screen, but it was trying to show things in 3D, and you could move it around to see the molecules from different directions. But you're always working on a 2D screen.
Okay. Thank you.
I have another problem. I have another question. Why do you think the student A and B in the first column does not improve after IVR? Do you guess the reason?
Yes, we think that the problem was that their knowledge of chemistry was so poor that when we were giving them things to do, they weren't understanding what they were doing, and so they couldn't build their knowledge. They just were trial and error and bumbled through the activity. They didn't know what to learn because they didn't know enough chemistry. And so we found that with those students, what we should have done was, before they went into virtual reality, give them a half-an-hour tutorial on the fundamentals so that they could learn. But the study was, we're looking to see how VR could be used. And we discovered that for the very weak students, it doesn't work very well unless you provide more scaffolding.
Yeah, students need more tool or more concept before learning.
For example, if we gave them, there are model kits you can buy that have models of water molecules with magnets. And so they stick together to demonstrate hydrogen bonding. If we gave them a little tutorial with those, we think that then they would improve in this section. But at the time, we didn't know. This is something you learn from doing the research.
Did you say when it's the same thing occurred that more poor concept students cannot learn through using VR, or even though some real physical model?
I think the if you don't have enough knowledge, it's hard to build on what you don't know. So what we should have done was, with the students who were very poor, given them some more information before they entered virtual reality, because in the virtual reality, we were assuming a certain level of knowledge. The students did not have that level of knowledge. Some of them couldn't bridge that gap. If you already had that level, then you could build and learn more. But if you don't have that level and it's too low, you can't bridge the gap. And so what's happening at this level is just, okay, you can press the buttons and have things happen, but you don't understand why they're happening.
It's my guess, just my thinking, and I think VR has some weakness in time. So the students can feel more fatigued. Even I am trying to use this program, and I am studying with this program. It's more fatigue to eyes, and so it gives some kind of it distracts to their learning. So with just using physical model, we can give them more time to experience, and there's no obstacle like giving fatigues to their eyes. So I think that kind of weakness, technical weakness in VR, when it is improved, we can give more percentage of getting lower concept students to do more better concept students.
I think the issue is, we try to keep the VR activity to about 30 minutes, no more than 40 minutes at a time, because we were concerned of them being in VR for too long. For the very weak students, we would give them something to do before they entered VR, not something extra within VR. So the VR session will keep to a certain length. Some very good students finished in 20 minutes. Some students explored for longer and tried lots of things, even the good students, but no one was there for more than 40 minutes. And the weak students were just pressing the button. So some of those finished reasonably quickly, but they didn't take anything away.
Yeah.
Okay.
Okay, thank you.
Let's move to the next slide. Otherwise, we'll be here till 11.
Okay, sorry.
Okay. The taste receptor was again trying to get the students to understand the importance of shape and charge for chemistry, and particularly chemistry of biological systems, because in this case, the shape of a molecule is very important for its biology. So when we teach stereochemistry is chemistry of three-dimensional shape. And there are many molecules where the mirror image form of the molecule is different to the original. Just like your left shoe is a mirror image to your right shoe, and they're different. But a drinking glass and the mirror image are exactly the same. So some molecules have the mirror image is the same as the original, like, for example, a drinking glass. But other molecules, like your shoes, one form is different to the other. Even though they're just mirror images, they have very different properties. Your left foot does not feel comfortable in your right shoe. And so we wanted them to understand the importance of shape.
네, 제가 중간에 잠깐 끊겨서 잘 이해했는지 잘 모르겠는데, 그 화학적인 이제 이런 것들이 또 바이올로지컬한 이제 생물학적인 것에도 너무 중요하게 작용을 하고, 또 이런 그 분자 어떤 그 쉐입이라든지 모양이라든지 이런 것들이 워낙에 중요하기 때문에 중요하다라고 말씀을 하시면서, 이게 이제 이체화학 스텔라 케미스트리 이거는 이제 3D로 공간에서 이제 시각화하는 것을 이제 배우는 건데, 마찬가지로 그 모양에 중점을 둔다 하면서 우리가 이제 5월은 좀 제가 이 부분 이해를 잘 한지 모르겠어요. 그 오른쪽 신발과 왼쪽 그 발에 서로 그 신발이 서로 다른 모양을 하고 있고, 이거를 서로 다르게 신으면은 그게 굉장히 불편하게 느껴진다라고 말씀을 하셨던 것 같은데.
네네.
네.
저희가 받아서 설명 좀 구체적으로 드리면, 제 거울 모양으로 해서 대칭인 그런 게 있는데, 이제 모양이 거의 비슷해 보이긴 하지만, 왼쪽 신발과 오른쪽 신발처럼 비슷해 보이긴 하지만, 전혀 다른 성질을 띈다. 아까 막 설명했듯이 다음 슬라이드에서 나오는 그런 쓴맛을 내는 성질과 이제 단맛을 내는 성질이 이제 비슷해 보이지만 다르게 낸다라는 것을 얘기하는 것 같습니다. 네.
Okay, so these were the two molecules we looked at, and phenylalanine is an amino acid. Amino acids are the compounds that make up proteins, and L-phenylalanine is a naturally occurring form. D-phenylalanine is not naturally occurring, but it's sweet. It's part of the compound aspartame that's used as the sweetener in things like Coke Zero and things like this, Diet Coke, Pepsi Zero, I don't remember. So these are the two molecules we used to teach this concept.
저희가 이제 이 두 가지의 이 분자 구조 같은 경우에는 왼쪽에 있는 거는 뭐라고 읽어야 되는지 잘 모르겠는데, 네, L페닐알라닌이고,
페닐알라닌. 네.
네, 그리고 오른쪽에 있는 거는 D페닐알라닌인데, 이제 왼쪽에 있는 것과 오른쪽에 있는 것이 이제 왼쪽은 쓴맛을 이제 자연적으로 이렇게 되면서 쓴맛을 내는 거고, 그리고 오른쪽 같은 경우에는 이제 그 방금 전에 말씀하셨던 것처럼 단맛을 낼 수 있는 이런 건데, 이게 다이어트 코크나 아니면은 이제 코카
지금 네, 수민쌤이 살짝 튕겼었어요. 네, 다이어트 코카나 막 이런 것에서 나오는 이제 이성질체이고, 그다음에 거기 아까 여기 윤용근 선생님께서 이제 보내주셨었는데 이 거울처럼 무드로 되어 있는 그런 이성질체라고 한답니다. 네, 넘어가겠습니다. No.
Okay, I'm sorry. I got confused with things are changing.
Sorry.
Okay, so what we wanted the students to learn in this one here was getting an idea of the shape. And we got them to move around. They built the two molecules in virtual reality, and then they placed them inside a taste receptor, and they had to look around, walk around and look to see how they fit. So they were using action and to understand what's going on.
이 아이들이 여기에서 배웠으는 것은 이 두 분자를 빌드, 즉 만들어가지고 테이스트 리셉터, 즉 그 감각을 수용하는 이제 그 맛 수용체에다가 넣어서 어떻게 작용하는지를 직접 이렇게 돌아다니면서 보는 거를 이제 의도를 하셨다고 합니다. 그래서 이 안에 액션이라든지 이런 것들이 들어가게 되는 거죠.
Okay, so this is what we did. We got them to make the two forms, identify electron-rich and electron-poor areas, and then place that into the reactive site to determine which one fits properly. And the video will show what they do.
Touch gently.
We have that. Oh, okay.
Oh, wow.
Oh. So this is taste receptor. Maybe we should put one of them here. Let's put the L one. Do you think it's fit?
Does not fit.
It's not fit.
The hydrogen is in the way.
Yeah.
It doesn't really fit very well.
Let's try another one. That one, yeah.
Yeah, it fits.
Yeah, it
better.
fits. It fits better.
So with this video, again, it doesn't look so good on 2D screen, but on the 3D, when they walk around, they can see that one goes all the way in and fits properly. The other one doesn't fit so well. And so then they can recognize that the L variety is not the right variety. D-phenylalanine is the sweet form.
한번
네. 여기에서 이 두 가지의 이제 이 분자의 형태가 각각의 여기서도 설명하셨다시피 맛을 느끼기 위해서는 올바른 분자가 올바른 수용체에 맞아야 되는데 어떤 것이 맞는지를 지금 학생들이 직접 이제 영상에서 하고 있는 모습을 보이면서 L이 이제 한번 넣어볼까 했는데 이거 핏하지 않는데 즉 맞지 않는데 라고 얘기하면은 그 다음 대에는 D를 한번 넣어보고 이렇게 하면서 2D에서는 사실 구현이 굉장히 어렵지만 아이들이 직접 학생들이 직접 돌아다니면서 무엇이 맞는지 직접 한번 넣어보고 어떤 게 작용이 되는지 이런 것들을 직접 보는 것들을 통해서 그러면은 L이 지금 L을 넣어봤을 때 이게 쓴맛이겠구나 혹은 이게 단맛이겠구나 이거를 직접 직접 보면서 혹은 걸어다니면서 이렇게 해볼 수 있다라는 거를 동영상을 통해서 설명을 해주셨습니다.
Thank you. The final activity we had was a protein visualization. And acetylcholine esterase is an important enzyme that involved in neurotransmission. And so we got them to look at acetylcholine and the enzyme that's involved in the body that splits that apart.
아세토콜린 제가 설명드리면 단백질이 어떤 효소 기질 반응이 일어나는 거죠. 아세틸콜린이 어떻게 억셉터에 들어가는지 여부를 이제 3D로 구현하는 것입니다. 영상 보여드리겠습니다.
So, can you change representation?
Oh yes.
Yeah.
This is ball and stick.
Yeah. Do we have another?
Yes.
This is
Cartoon.
this is colorful. Nice.
The ribbon.
Do we have another one? Maybe the one that show electron poor and rich. Yeah, this kind of show it. Yeah, I like this.
This is the best if you want electron-rich areas and electron-poor areas.
Yeah.
Yeah.
Okay.
극성인 부분이랑 전자 극성인 부분이랑 막 이제 극성이 마이너스인 부분이랑 이런 것을 표현해주고 있는 것 같고요.
Let's see. From my view, I have to angle this a bit so that it can.
좀 살짝 깨지는 것 같습니다.
From my view, I have to angle this a bit so that it can go through because it's a tight fit. So
this looks really tight.
It like that.
Yeah.
And then
angle it like this, maybe.
Yeah. So the electron-rich region of the catalytic chamber will be close to the electron-poor region of the molecule, so it can hold it in place.
Yes.
And then this is the part that we want to react. So I'm happy with this.
Yeah, me too.
So, thank you. What did we learn from these 3 activities? The first thing we saw, the students all said, wow, they really enjoyed the activities. Most of them underestimated how long they were in virtual reality. We asked them, their typical answers were 15 minutes, 20 minutes, where in most cases they were twice that. So as far as learning was concerned, the students after virtual reality understood hydrogen bonding to a much greater extent. They could explain it in a 3-dimensional aspect as opposed to what was typically described on paper in 2 dimensions. For the stereochemistry, they could now identify a D and L stereoisomers, something that was not taught in class. And they could explain why the shape and the charge is important in biology. And in the proteins, they recognize the complexity of an enzyme, and they also could explain why an enzyme was such a good catalyst.
아이들이 맨 처음에 나왔던 것처럼 이제 어떤 결과들이 어떤 좋은 점들이 있으면은 먼저 첫 번째로 아이들을 반응화 이렇게 하는 것에서 정말 많이 즐겼다라는 거를 아이들이 정말로 즐기면서 이 활동을 했다라는 걸 알 수 있고 15분, 20분 안에 이런 것들이 이제 일어났고 그리고 두 번째로는 아이들이 이제 그 결합에 대한 거, 그 모양이 왜 중요하고 어떻게 이제 형성이 됐고 하는 것들을 훨씬 더 이제 잘 설명을 할 수 있게 되었습니다. 또 입체 화학과 관련해서도 2D에서는 사실 불가능한 혹은 종이에서 배우거나 하는 것들이 불가능한 이런 것들을 아이들이 입체 화학을 직접 입체적으로 그 가상현실에서 볼 수 있었고 교실에서 이제 가르치지 않았던 어떤 D와 L, 그 어떤 관점들 이 다르고 어떻게 모양이 다르고 어떻게 이런 것들이 되는지를 마찬가지로 설명을 할 수 있게 되었다 이렇게 얘기를 해주셨습니다. 어째서 이 본드나 결합이나 모양이나 이런 것들이 왜 중요하고 하는 것들을 아이들이 직접 경험을 통해서 배울 수 있었다 이렇게 설명을 해주셨습니다.
Thank you. This is the group who did the work, and me, but I took the photo. The two PhD students are the small lady with the orange sash. She's from Indonesia. The other PhD student is Henry from Uganda. The group leader was Mihei Won, originally from Korea, but now at Monash. David is the senior leader of the group in some respects. He's the mentor. Chin Chong is from Taiwan, who's a researcher in technology in education. And Roy from Sydney is an expert in visualization in chemistry. So that was a team. And I was just a chemistry educator. So, and what did we learn from this? What's the take-home message? Take-home message that for me is that we want the students to recognize that chemistry does not happen on paper. That's how we usually examine it, on pencil and paper, or pen and paper. But we want them to come to the realization that it happens in a reaction vessel. That reaction vessel could be a flask, but it could be the atmosphere, it could be a river, it could be your body. Chemistry happens with lots of other molecules around. It doesn't happen on a piece of paper with just the appropriate molecules. And we want the students to learn to imagine what is happening at that microscopic level. Now, VR can't do all the types of chemistries that are possible, but VR, I hope, can help train the mind to start thinking about molecular level. And if they get into the habit of thinking about the molecular level, then we don't need VR for everything. Experienced chemists and chemical researchers can think of that at that molecular level. And when we learned there was no VR, I'm hoping that VR can help the students visualize at that level quicker, at an earlier stage.
네. 여기서 마지막으로 얘기를 해주신 게 화학은 그냥 말 그대로 한 장에 이제 종이에서 일어나지 않고 탐구되는 곳에서 일어난다라고 얘기하시면서 분자가 움직이는 반응 용기에서 발생한다라고 말씀을 하셨어요. 이 반응 용기라는 거는 어떤 플라스카드가 될 수 있고 강이 될 수 있고 혹은 우리의 몸이 될 수도 있고 이런 것들은 모두 분자가 있는 어떤 곳에서든 일어날 수 있고 다만 종이에서 일어나는 것이 아니라 즉 종이를 통해서 배우는 것이 아니라 탐구되는 여러 가지 그런 곳들, 분자가 이제 그 작용을 하는 어떤 곳에서든지 일어날 수 있다라고 얘기를 해주셨습니다. 그러면서 이런 아이들이 가장 중요한 것은 분자적인 강점에서 즉 아까 초반에 설명하셨던 정말 이제 그 초미시적인 그런 그 레벨에서 아이들이 생각을 할 수 있어야 되는데 VR이 그것의 첫 시작이 될 수 있는 희망이 된다라고 말씀을 하셨습니다. 분자적인 관점에서 아이들이 첫 그 생각을 해내고 거기에서 어떤 일들이 일어나고 있는지 그 첫 시작이 되는 것이 아마 그것을 시각화하고 그 레벨에서 생각하고 하는 것의 첫 시작이 VR이 될 수 있다라고 얘기를 해주셨습니다.
Okay, thank you very much, Sumin and Sop for your translations, and thank you very much for the questions that I received, and thank you for hanging around for an hour and a half to listen.
감사합니다. 혹시 용근쌤 질문, 네.
Would you mind if I ask you something?
Yes, certainly.
Yeah. First of all, I appreciate your lecture. I found the lecture on using VR molecular model teaching very interesting. It is an area I'm passionate about. While I had implemented the hands-on activities in VR before, so your lecture, I learned how learning occurs through question generation and answering processing collaboratory activities.
Mm-hmm.
May I show firstly you activity ID?
Sorry?
May I show my character ID? Show
Yes, yes.
you? Yeah.
Mm-hmm.
화면 공유 될까요? 잠깐.
네네, 당연하죠. 네.
Yeah.
네,
보이나요?
네, 보입니다. 네.
This is molecular model, 4D frame.
Oh, yes.
화면이?
With magnets?
보입니다.
Yeah. Do you know 4D frame? I made molecule 4D frame. This is cellulose molecule and the glucose starch molecule.
Yes, yes.
This is you explained yes. This is D-alanine. This is L-alanine. So I made the nucleic acid. So I made the amino molecule.
Wow.
This is a DNA molecule.
Mm-hmm.
Yeah. So I have curiosity. What do you think the difference between using a virtual environment versus the physical mode, this model, or primal model?
The physical model is great for single molecule situations. So it's and kind of nothing beats hands-on of doing a single molecule. Making a DNA, for example, takes a lot of time, but I think to make it in virtual reality would also take a lot of time, unless you had some sort of automation happening. But if you've got a physical model that's big enough, you can walk around, you can do it. The process of building the molecule is really important, whether you build it in virtual reality or build it as a physical model. That process of building it is important, because if you're just given the molecule, your mind is not thinking in the same sort of way. You're just looking at something. But if you've got to put it together, then they have to make decisions. And so either way, they both work well. The advantage of virtual reality is, for example, when we're looking at snowflakes, when you've got a large number of molecules, it's very hard to do with models. Making an ice lattice with 150 water molecules will take a long time. But we got the students to build sections, and then they put it all together in one shot. So they then had 150 molecules. Virtual reality also gives you the advantage, for example, in a protein, you can walk inside a protein. you can't do that with a molecular model unless it's enormous size. And you can then interact with the protein and its substrate. And that's something you can do in virtual reality that I don't think you can do anywhere else. Even on a 2D screen, you can't walk inside a molecule. You can zoom in, but you're always looking at a 2D screen. So I think that aspect is valuable. I don't, and we tried to stay away from the concept of just making a L-phenylalanine and observing the stereochemistry between those two, because you can do that on a 2D screen. You can do that with molecular models. We wanted to do something with it and show how the charge and the shape played an important part in the chemistry. So that was something you couldn't do on a 2D screen.
And so a basic step is with the lecture with the physical model, and then next step is a VR model.
Yes, we did that with what we do in the VR is different to they'll do a physical model, putting things together, and then of a molecule, and then in VR they will use something different. And then when they come out of VR, we check what they've learnt by doing it again. So,
I have one other question. What do you think VR model or primal model?
primal models.
Yeah, primal.
They're quite good. We use those in our first year teaching. Strangely enough, we don't use VR in our first year teaching because we don't have enough sets and we don't have that technology advanced well enough. An advantage of the models is you don't need a lot of technology. You also don't need a lot of training. The students can learn how to use it fairly quickly. Virtual reality is getting better very quickly. And I think that soon, maybe in the next 5 years, this will become more commonplace. Hopefully in less than 5 years. It's even the gap from 2000 to 2024, 2020 and 2024, the technology has advanced so quickly. It's our technology is 4 years old and seems very, very old.
Thank you very much.
And I have an opinion add to Mauro's opinion. And when we use VR, we can float the model, float model. Not it's not possible in reality situation. And secondly, we can change the shape, what we see in the molecular. As you can see in the video, we can change the frame to the 3D 입체적인 뭐지? stereotype model, and we can change other type of model like 분자 모형이지만 좀 다른 이제 뭐지? 확률로 돼 있는 그런 이제 more polar and non-polar type model. We can change the shape what we see. I think that is the strength of VR education. Okay. 혹시 뭐 의표쌤
very much interesting lecture.
Thank you. It's been a pleasure.
네네.
I have one question. One of my worries nowadays teaching students is that
수민쌤 자꾸 끊겨. 어떡하지? 수민쌤 지금 끊겨가지고.
Next time I use VR model.
혹시 되나요, 지금?
지금
지금
돼요.
돼요.
네네.
네. Actually, I used VR mostly as a reconfirmation of what I taught at the textbook. But sometimes my worries nowadays is there are some students that really lack of like learning motivations, but actually they love VR so much because they enjoy like wearing like stuff, goggles and doing stuff. So I was wondering if you mentioned about really poor students. Is it? But I thought maybe those students can, starting from like zero, starting from nothing, they can also learn something, learn knowledge one by one by the VR. I was hoping, but what you mentioned previously, I was thinking maybe is it really necessary? Is it inevitable to teach by textbook first and do the reconfirmation at the VR? I was wondering, is it necessary to teach like knowledge first and then do VR as a reconfirmation, or maybe I was hoping we can just do gain knowledge one by one just by the VR. I was hoping, yes.
Well, it kind of depends on the VR program. Our program was this: we want them to learn a concept, and we started from a level of knowledge that was, for some students, too high. These were surprisingly very weak chemistry students, disappointingly weak. And so we assumed that they knew this basic high school chemistry, and that these small number of students didn't know the basic high school chemistry for water chemistry. So they couldn't understand where we were starting at this level. A lot of people have used virtual reality, and again, it depends on how you use it. If you use it to, here is a phenomenon, here is a concept that's really curious, and they can explore in virtual reality to stimulate their curiosity, then you go to textbook to teach the stuff in maybe not so a fascinating way as virtual reality can do, but you've already stimulated their curiosity. You've shown them the problem and something phenomenal, and that might be a flower blooming, and why does it bloom at this time, or what happens, how does a bee pollinate it? And so you can show them that VR and then get them to understand the science behind that process later, but you've got their curiosity, you've made them want to learn. So it can go both ways. A lot of people use VR as a motivational.
Thank you.
동기부여 어떻게 알아요? 그 부분만 딱 못 알아듣겠어. 그러니까
제가 여쭤봤던 게 아이들이 정말 부족한 아이들 같은 경우에는 방금 전에 너무 못하는 애들은 VR을 해도 일정 수준을 안 된다고 하셔가지고 저희 반에 그런 애들이 많은데 프로그램 바이 프로그램인데 그래도 동기유발에서 미리 꽃이 언제 피고 왜 피고 이런 것들을 먼저 모티베이트를 한 다음에 그 다음에 이제 텍스트북 교과서로 돌아와서 그럼 언제 했는지를 알아보자, 이렇게 먼저 VR로 보여주고 이제 동기유발을 하고 그 다음에 이게 왜 그랬는지, 여기서 꽃이 이때 폈다 하는데 왜 그랬는지 우리 교과서로 한번 알아볼까? 네, 이런 말씀이신 것 같아요.
백월드로 할 수도 있다는 것을.
네네네.
Yeah, I agree with your Mauro's opinion, and we can make program that can teach low-level students also.
Yeah. It just, you pitch it at the right level. We pitched ours at the wrong level for some students, but it was at the right level for most students. So we had to, those who were not at that right level, we should do something to bring them up rather than rewrite a separate program for them. So again, I think it's important to know what your students can do before you put them into virtual reality. And we didn't know that so well when we assumed this is the level they were starting at. But I think with the teach by textbook and using virtual reality as a reward or a reinforcing of the concepts also works very well. If it's there to help tie together what you taught from the textbook, or help them to see what was in the textbook in a different way, which would help them remember. And learning is helping students put things in their long-term memory that then they can use for other learning.
How can I access the VR program? Your Mauro's VR program?
It's not ready for general distributions yet. I think what we would like to do is make it reconfigure the program so we can put it on something like a Meta headset. And so we don't need the HCT Vive infrastructure, and put it on a headset that's portable. And we need to remove a lot of bugs that are currently still in the program. The program worked well because the 2 PhD students were very good at making it work. But it still needs a bit of work. I hope to make it available to others to use, but it'll be in a form that would work on a portable headset like a Meta Quest, where you don't need to have a high-level computer talking to the headset.
의표쌤 혹시 좀 질문하실 점 있으실까요? 없어요? 혜린쌤 혹시 질문 주실 수 있으실까요?
아니요, 잘 들었습니다. 감사합니다.
오케이.
저 그럼 마지막으로 하나만
네.
할게요. I have one basic question. In Korea, the word XR is generally used in education and industry, while the word immersive learning is common in other countries. So, what do you think about differences between two words? Is it the same meaning?
I don't know the XR meaning. I thought it was a logo or a group name that you had thought about. I didn't know that it was the term you use for that immersive virtual reality world. Virtual reality, some people group the whole thing with virtual reality, augmented reality, and the other forms of that sort of reality. We define that in our situation as when it's immersive, you're in a new world and not distracted from the outside world. So augmented reality, you can see things in this virtual space, but you also see the outside world. So the outside world can distract you. It can add the pluses and minuses. Augmented reality allows you to do things with something and apply it to a real world situation, like, for example, learning safety in a laboratory or something of that effect, where you want them to see the lab. But in other cases, immersive virtual reality, where you want them just to focus on what the learning objective is and not be distracted by things happening outside, that can be an advantage. So it depends on your purpose.
Thank you.
I hope to see as soon as possible. I appreciate you sharing your great knowledge. And we talk AR, VR put together, and we extended reality in Koreans. And
XR is extended reality.
Yeah, it's the meaning of extended reality. Okay. 더 얘기하실 분 계실까요? 네, 긴 시간 너무 감사드리고 수민쌤 없었으면 큰일 날 뻔했어. 와, 너무 고마워요. Thank you for Sumin for translating
Yes,
our
thank you very
speech.
much. Yes.
And 너무 감사합니다. 고생하셨습니다. 네, we will keep this meeting.
Oh, thank you very much. It's been a pleasure to meet you all. Even though it's only virtually, it's still a pleasure to meet you all. So, and thank you for the interaction.
Thank you so much. See you. 감사합니다.
Thank you.
Thank
See you very
you.
much.
See you later. Thank you very much.
Good
Thank you.
night.
감사합니다.
감사합니다.